Concavity. A function or its graph is called concave upward on the interval I if f prime is an increasing function on the interval I. It is called concave downward on the interval I if f prime is decreasing on the interval I. Okay, so notice in the figure below that the slopes of the tangent lines increase from left to right on the interval between A and B. So decreasing, decreasing, and then increasing. So f prime is increasing, and the function f is concave upward, abbreviated CU, on the interval of AB. Now, it can be proved that this is equivalent to saying that the graph of f lies above all of its tangent lines on AB. Now, similarly, if we look at the interval between B and C, the slopes of the tangent lines decrease from left to right. So now it's going to be decreasing. And so f prime is decreasing, and f is concave downward, CD on BC. Now, a point where a curve changes its direction of concavity is called an inflection point. And so the curve here in this figure changes from concave upward to concave downward at point P. So this is concave up and then concave down. And then from concave down to concave up, we can see that there's a point here at Q. So we can call both P and Q our inflection points. Now, because the second derivative is equal to the derivative of the first derivative, we know that if the second derivative is positive, then the first derivative is an increasing function, and so the function f is concave upward. Similarly, if the second derivative is negative, then the first derivative is decreasing, and so f is concave downward. Thus, we have the following test for concavity. The concavity test. Part A, if the second derivative is greater than 0 for all x in that interval, then the graph of f is concave upward on that interval. If the second derivative is less than 0 for all x in the interval, then the graph of f is concave downward on that interval. So let's continue what we were doing from that example that we've done previously. Okay, we were given the function f of x, which is equal to 3x to the fourth minus 4x cubed minus 12x squared plus 5. We found a derivative to be the following. So let's go ahead and find the second derivative. So if we find the second derivative, we get 12 times 3, which is 36, and that's 36x squared. This gives us minus 24x, and this gives us minus 24. Okay, so what can we factor out of these three terms? So we can factor out a 12. So if we factor out a 12, we end up getting 3x squared minus 2x minus 2. Okay, so now what we're going to do is we're going to set this equal to 0. So we have 12 times 3x squared minus 2x minus 2, and we're going to set that equal to 0. And then we divide both sides by 12, and we get 3x squared minus 2x minus 2, which is equal to 0. So now, when we want to factor this, we can't factor it without either completing the square or using the quadratic formula. So in order to factor here, we're going to use the quadratic formula. And using the quadratic formula, we get the following values. We get x, which is equal to 2 plus or minus 2 times the square root of 7 over 6, which then gives us 1 plus or minus the square root of 7 over 3. Okay, so that's going to give us two values for x. Okay, and if we round it to one decimal place, we get one x value to be 1.2, and the other x value is going to be negative 0.5. Okay, So now, what happens next? Well, these two values for x now represent the critical numbers for the second derivative. So what we want to do is now we want to be able to look at the regions for this. So we know that for the second derivative, we're going from negative infinity to positive infinity. We have 0, we have negative 0.5, and we have 1.2. And again, that's created our regions here. So we have 3 regions. And that's going to tell us what's happening, whether it's concave up or concave down. Okay, so we can see that in region 1, the interval goes from negative infinity to negative 0.5. We know in this interval it goes from negative 0.5 to 1.2. And from here it goes from 1.2 to positive infinity. Okay, so in region number 1, we can pick a value in region number 1. Well, let's pick x equals negative 1. Okay, and then we're going to plug it into the function, which is the derivative. So, which we're going to plug it in there. So we're going to have 12 times 3 times negative 1 squared minus 2 times negative 1 minus 2. So we multiply that all out, we get 36, and we can see that's going to be greater than 0, which tells us that it's positive in region 1. Okay, if we take a look at region 2, we can pick the value of 0 for x. So we have 12 times 3 times 0 squared minus 2 times 0 minus 2, and that gives us negative 24, and we can see that that's less than 0, so it is decreasing there. And then in region 3, we can pick x to be equal to 2. So this is going to be 12 times 3 times 2 squared minus 2 times 2 minus 2. And that gives us 72. And we can see that's greater than 0, so therefore it is positive. So what is that telling us? So we can see here that this tells us that the second derivative is positive. And if it's positive, then that means it is concave up. Okay, here we can see that the second derivative is less than 0. So therefore, this is concave down. And then here we can see that the second derivative is going to be greater than 0. And so therefore, this is concave up. So now this next statement, it says, in view of the concavity test, there is a point of inflection at any point where the second derivative changes sign. A consequence of the concavity test is the following test for maximum minimum values. So let's go back up here and then determine what are the inflection points. Well, we can see here from region 1 to region 2, we go from positive to negative, and that point is the inflection point is negative 0.5. Okay, and then if you look here from region 2 to region 3, again, the sign changes from negative to positive. That's where the sign changes. So the other inflection point is 1.2. Okay, now the second derivative test, suppose the second derivative is continuous near c. So if f prime of c is equal to 0, and f double prime, or the first derivative at c is equal to 0, and the second derivative at c is greater than 0, then f is a local minimum at c. If f prime of c, or the first derivative, is equal to 0, and the second derivative at c is less than 0, then f is a local maximum at c. So let's go ahead and use the previous example before we go any further here to determine what the local minimum and local maximum is. Okay, so let's use the second derivative test from our example. So from our previous example, I'm going to show you the work that we have already done. We have found the first derivative, and then we found the critical numbers of those derivatives. Okay, and then here are the critical numbers. Okay, and then also let's keep in mind that our graph shows our critical numbers. Okay, so here we have a critical number at -1, another critical number at 0, and another critical number at 2. So each one of these, okay, if we take a look here, if we look at part A and part B, okay, each one of these, if we found f prime of 0, that gave us 0. F prime of -1 is 0. And f prime of 2 was also 0 because those are the critical numbers. Okay, now what we want to do is, in step 2, we want to use the second derivative. So the second derivative from up here was 36x squared. And that's minus 24x minus 24. Okay, so let's go ahead and we want to plug in f double prime of 0. So we get 36 times 0 squared minus 24 times 0 minus 24. And that is equal to -24. We find f prime of -1. That's 36 times -1 squared minus 24 times -1 minus 24. So this becomes positive 24 minus 24 is 0. We get 36 times -1 squared, which is positive 1, so we get 36. Okay, and then let's find f double prime of 36 times 2 squared minus 24 times 2 minus 24. And that gives us 72. So we can see that this is less than 0, this is greater than 0, and this is greater than 0. So we can then say that f double prime of 0 is less than 0. And here we can say that f double prime of -1 is greater than 0. And f double prime of 2 is greater than 0. So, looking at definition number 8 with the second derivative test, if f prime of c equals 0 and f double prime of c is greater than 0, then f has a local minimum. So if you notice here, this tells us that we have a local minimum at -1, which we can see from here. And then we also have a local minimum at 2. So we can see that we also have a local minimum. And if you look at part B, f prime of 0 is equal to 0 and f double prime of 0 is less than 0. So that tells us that we have a local maximum at 0. And if you look here, there is the local maximum. Go ahead and rewrite that. So there is the local max at 0. Okay, now if we take a look at part A, it's meaning that if f prime of c is equal to 0 and the second derivative of c is greater than 0, then f has a local minimum at c. So for instance, in part A is true because f, or the second derivative, is greater than 0 near c. And so if f is concave upward near c, this means the graph of f lies above its horizontal tangent at c, and so has a local minimum at c, as you can see here below. So this tells us that the second derivative at c is greater than 0 is considered concave upward.